Hello everyone, I am Murali Brahmadesam, Director of Engineering for Aurora Databases and Storage. Today I'm going to talk about Aurora MySQL compatibility in depth. What is Amazon Aurora? Amazon Aurora is a managed database service that gives performance and availability of high-end commercial databases with simplicity and cost effectiveness of open source databases. We have drop-in compatibility with MySQL and PostgreSQL, and today I'm going to focus on MySQL compatibility. It also has simple pay-as-you-go pricing. Let's dive in. Let's talk about performance. I'm going to talk about the write and read throughput and how Aurora is able to deliver 5x the throughput of traditional MySQL on a block device storage. And in this example, we are using Sysbench read and write workloads on R5 16XL instance type. As you can see, the write throughput of Aurora MySQL with 5.7 compatibility is able to do 200,000 write statements per second, while MySQL 5.7 on a block device storage like EBS, Elastic Block Storage, is able to do only around 20 to 25,000 writes per second, whereas MySQL 8.0 is able to do a little bit more than that, around 30,000 writes per second. So we're able to derive amazing performance compared to non-Aurora systems with similar instance type. Let's look at read throughput. Similar Sysbench configuration with the same sized database instance, Aurora MySQL is able to do close to 800,000 statements per second, whereas MySQL 5.7 is able to do less than 200,000 statements per second, and MySQL 8.0 is able to do around 400,000 statements per second. And in this presentation, I'll dive into how Aurora is able to achieve this performance. And I have an announcement in terms of us working on MySQL 8.0. It's in final stages, and we'll share the more information outside this presentation on the release. I'd like to talk about Amazon's AWS's own 64-bit ARM-based EC2 instances called as Graviton2. And in this graph, it's comparing the Intel performance, similarly sized Intel performance versus Amazon Aurora MySQL 5.7 on Graviton2. It's the same database engine running on two different architectures. In this case, the database workload is HammerDB, a typical TPCC workload on a R6G large instance. As you can see, Intel instance is able to do around 52,000 number of new orders per minute, whereas on the same workload on Graviton2, we are able to achieve around 60,000 orders per minute. So it's around 15% more. We see similar or better performance across all R6G instance sizes. Aurora preview on Graviton2 will be available soon. You might wonder, yes, we see a good performance. Is it consistent? Because if you have consistent performance, then you'll be able to tune your application better. In case of Aurora, we are able to get consistent performance that is 100x more consistent than comparable non-Aurora system. In this case, we are comparing the write response time in terms of millisecond. As you can see, Aurora is able to maintain around 100 millisecond for this particular benchmark run on R5 12XL over 10 minutes, whereas you see jittery performance on a non-Aurora system. The question is, how did we achieve this? By doing less work. So we do fewer IOs, we minimize the number of network packets, we cache prior results, and more importantly, we offload parts of the database engine to a purpose-built storage system that we'll talk a little bit more about in the next slide. And when we do less I/O, we also are very efficient in processing the requests. We process asynchronously, we reduce the latency path, we use lock-free data structures, we do batching operations together. So all the good engineering practices that we all know, we put in practice in Aurora system. Let's look at how the distributed system looks like. So our core philosophy is log is the database. And I'll go through the tenets here, and then I'll explain how it actually works. So the first thing is we offload redo processing to a distributed storage that spans thousands of storage nodes, write only logs and no database checkpoints. This is a big departure from traditional database systems, which relied on periodic checkpoints, and the logs are used for recovery. We use 4 out of 6 write quorum across 3 availability zones with 2 copies per AZ. And we'll talk a little bit more about how it helps us to achieve better availability as well. So in terms of architecture, the lower half in the diagram, you see shared storage volume. That is a purpose-built storage system that is built for databases. And what I mean by purpose-built is that it understands log records and pages. And this spans across 3 availability zones, and you see 2 copies per availability zone. And we have multiple database instances that customers can configure to be attached to the same storage. So that's what we call as multi-attach storage system. And the storage system itself is multi-tenant, and it shards the storage into 10 GB segments and spreads it across thousands of storage nodes, which have local SSDs. So this is a very custom purpose-built storage system built for databases, and Aurora uses it. So in case of the writes that are performed by a database engine on the distributed storage system, only log records are being sent. So the log records are much smaller than database pages, and there's like hundreds of bytes compared to 16 kilobyte sized pages that MySQL uses. So we do very less I/O compared to traditional database systems. And we don't do checkpoints. So if you don't do checkpoints, you might ask, if the log is the database and you don't do checkpoints, is it going to impact read performance? The way we address this problem is by pushing down that capability into the distributed storage system, which continuously performs checkpoints on behalf of the database engine, thereby reducing the network I/O and also the CPU that is required by the database instance itself to perform these tasks. So this is the key concept of Aurora. By doing less work and making it very efficient by pushing down the database functionality to a distributed storage system that is purpose-built for databases. So now that we saw how the write throughput is achieved, can we do more with this distributed system? And the answer is, of course, yes. And what we did is we launched a feature called as parallel query. And that is done by pushing down query execution on top of the storage system. Aurora database, as we saw, is hosted on top of thousands of storage nodes whose CPUs are used for query processing now. The database engine itself identifies a portion of the query that can be pushed down to the storage node, and it processes the query. The storage node processes the query on the rows that are resident locally. As I mentioned, the storage volume is split by 10 GB segments and spread over thousands of nodes. So each storage node is processing on the 10 GB shard of the database. The storage node returns result sets that are then aggregated on the database node. So the benefits are obvious. We are moving processing closer to the data, significantly reducing the network traffic and the latency. Without parallel query, the database engine has to pull in the database pages from the storage if it's not resident in the memory already, and then process it. So that means that it is incurring a lot of network I/O and CPU to process the query. Whereas in case of parallel query, thousands of storage nodes are doing the job in parallel. What are the capabilities that we currently have? The current capabilities is ability to push down filters, to push down projections and expressions. And I'm excited to say that in the upcoming engine release, we're adding capabilities to do a little bit more than that in terms of pushing down aggregations. We have multiple operators. We do group bys. We support partition tables. We support a lot of large objects. And we also support tables that have been modified by Aurora, MySQL, Fast Online DDL. Now that you saw the capabilities of the system and how it scales, let's look at the performance results. In this slide, I'm showing the results of a TPCH benchmark, and there are 22 queries, and this bar graph is showing how much parallel query is faster than a non-parallel query execution. For example, query 1 is able to show a performance gain of 125x, and query 6 is able to show 180x performance gain. As you can see, there are several queries that parallel query is doing much better than a non-parallel query execution, and there are queries that we are not still able to push down, that we are constantly working on. Now that we talked about performance, you might be thinking, how does Aurora scale? Let's talk about scalability. We used to support database sizes up to 64 terabytes, and we recently launched the ability to support databases up to 128 terabytes. And we are able to scale to 128 terabytes without sacrificing the performance and also all the features that Aurora already has. So your existing databases can scale up to 128 terabytes, and you don't have to re-architect your application if you're closer to the previous limit of 64 terabytes. And this is something that is very unique. You don't have to pre-configure the storage system. The storage system automatically scales up. And you might be wondering, what happens if I delete the data, right? Will you scale down? Yes, you're able to scale down now with the new functionality. So database engine informs the storage system about the freed space, and the storage system actually frees the space. Let's look at that in a practice example. So in this case, the graph is showing, the x-axis is showing the runtime, and the y-axis is showing the bytes used in gigabytes. In this example, the database, we added a couple of tables, T and T1, and we constantly added data. It reached close to a terabyte in size. And at some point, dropped the table T1, in which case the database engine informed the storage system on each page that has been released by the database, and the storage system released it, and it is showing the newer utilization, which is almost half of the size, using the CloudWatch metric volume bytes used. So you will be billed only for the space used now. And after some point, the table T is also dropped, and you can see that the database engine is now able to release all the space. This is a very unique feature that is very hard to implement in a traditional block device storage, where the provisioning would not easily allow to release the space. But because Aurora has a special purpose-built storage system, we are able to do this by releasing at a page level. So you can immediately release the storage if you drop the table or you delete rows. So we talked about performance, we talked about scalability features, and what about availability? If the database is not available, performance and scalability doesn't matter that much. So let's look at how Aurora tolerates AZ+1 failure. As described before, by now this architecture will be very familiar. You have storage nodes with SSD spanning 3 availability zones, and we replicate 6 ways with 2 copies per AZ with write quorum of 4 out of 6. And I'll talk about read quorum of 3 out of 6 that is used for repair. Let's take an example where an AZ fails. If an AZ fails, there are still 4 out of 6 nodes available. So the database engines, the writers that are operating in availability zone 1 and 3 will continue to have 4 out of 6 copies available, and they continue to write. So there is write availability exists. For the database writers that have been placed in availability zones 2, they would fail over to one of these availability zones, and then they continue to write as well. So it's a failover, and the write availability continues to be available for them. What happens if a AZ+1 failure? AZ+1 failure is a non-zero possibility because we have thousands of storage nodes. There are a lot of hardware and software deployments might happen and so forth, in which case AZ+1 failure might happen, in which case if there is a hard failure, we still have 3 nodes that have the data. There is no data loss, and we quickly repair them, using the peer-to-peer replication protocol that we have and recover the write availability. So there's no data loss, and Aurora tolerates AZ+1 failure. You might wonder, what happens if the database crashes? How long does it take for it to recover? In case of traditional database, as we saw, the traditional database periodically checkpoints, and on the recovery, it has to reapply all the redo logs. And depending on the configuration, it might be unbounded. And typical configuration is 5 minutes per checkpoints, in which case 5 minutes worth of redo logs need to be applied. And in case of MySQL, this is a single-threaded application that is applying all these logs. And there's a lot of seeks that happen in this process. In case of Aurora, the distributed storage system replaces the redo log record on demand, and it is parallel, it's asynchronous, and the database engine does not have to read the log records and replay it. The storage system does it. So the same amount of work is being done in a different way, in a parallelized way. So the recovery is quite fast. You might wonder, what happens if the database is going through a long running transaction, and let's throw in binlog as well. So binlog is a MySQL feature that is used for logical replication, and binlog is implemented in MySQL to contain in files, the logical data in files, and it contains only the committed transactions. So that means that the data, the logical data needs to be kept in memory or on the local storage of the database and flushed only when the database transaction commits. So in this example, you can see that if the long-running transaction had 1 GB worth of data that is being persisted, and if it crashes, the recovery time would be around 80 seconds. If it is 100 GB, it can be 9,000 seconds. So it becomes very hard for applications to tune if there is a failure if they use long-running transactions with binlog. We implemented a new feature wherein the binlog events are kept in memory initially until they reach the certain size, but then written directly to the distributed storage as a temporary binlog file with same durability guarantees. So across 3 availability zones with 4 out of 6 write quorum algorithm. It's the same durability that is given to the binlog file as well. But the key point to note is the data is being written as the data is being generated. And so we don't wait for the flush to happen until the commit happens. Upon commit, all we do is we close the current active binlog file and make the temporary binlog file as active file. So there is no data copy, there is no data flush, so there is no performance impact on the other ongoing transactions when the flush happens. Typically during this commit time of a long-running transaction, the network utilization is taken over by the binlog flush, and it doesn't happen with this feature. Upon crash recovery, the temporary binlog file is just dropped, and the recovery is much faster. And you can see that in the performance. We are able to do that in near constant time, 6 seconds to 17 seconds, depending on the size of the transaction. So if the crashes happen, Aurora recovers much faster. Let's look at the availability in terms of multiple reader nodes as well. So as I mentioned, this distributed storage volume is multi-attach capable. That means that we are able to attach 15 read replicas across multiple availability zones within the same region. So there can be one writer and 15 readers attached to the same storage volume for this database cluster. The writer, when it generates the redo log records, when it is sending it to the distributed storage for persisting for durability, it also sends that to the readers. And that makes it much faster to have the readers to be very close to the writer. And the typical lag we see is less than 10 milliseconds. You can also configure custom reader endpoint that comprises of a subset of the reader instances that you have in your database cluster. And you can point different applications to different reader endpoints. And that gives you a better performance because the reader instances buffer pool comprises of it's based on the queries that are being executed by the application. So if you have varying applications that you run on the same database, you can use different endpoints, and you get, by definition, scalability, you get load balancing, And if you have multiple readers, you can configure the failover order of the writer as well. So if the writer instance fails for some reason, it can fail over quickly to a different reader, and we already saw that the recovery is much faster. So let's look at how the application perceives the failure, if there is one. So let's look at a traditional MySQL installation, and let's use a better driver than the stock driver. In this case, I'm using MariaDB driver, which uses IP addresses instead of DNS. So it's much faster to detect to connect back. So in this case, this diagram shows that if there is a DB failure, it takes 15 to 20 seconds to detect the failure. This is the typical TCP failure detection that happens for the connection failures and retry attempts and so forth. And then MariaDB driver doesn't wait for DNS propagation, but the database has to do recovery. And we have already seen it depends on the workload and the configuration of the checkpoints and the log size and so forth. So this can be unbounded before the app can be run. In case of Aurora MySQL with the same MariaDB driver, the failure detection remains same, but the recovery is much faster. And MariaDB driver doesn't rely on DNS propagation. So the app can be run within 30 seconds of a failure. So if a hardware fails and we fail over and put a new instance, within 30 seconds your app is running. So we achieve faster failover with the Aurora technology. So you might wonder, can we do better? Of course we can do better with using RDS proxy. So the application stack, the overall stack would be like this. The lower half is very familiar. You have a writer instance, you have multiple reader instances talking to a distributed storage, but now you have a new layer called as Amazon RDS proxy to which the apps are connected to. So all the connections from the applications terminate with RDS proxy, and the RDS proxy is talking to the writer instance. And in case a failover has to happen, RDS proxy quickly reconnects into the reader instance. So the application connections are not dropped. So according to the application, the database is still up, but the instance has switched over underneath. And the outcome is pretty good. We're able to do 66% faster in failover time. In this graph, you will see that if the MariaDB driver is directly talking to the database instance, it will see around 15 seconds of recovery. Whereas if you use RDS proxy, you'll be able to see within 5 seconds. So this improves the availability much better. You might wonder, okay, all these things happens within a single region. What about multi-region? So we use Aurora global database functionality, and let's quickly look at the architecture. The architecture is familiar by now, where the writer is writing to a distributed storage fleet, and it is sending the data redo log records immediately as it generates to the reader instance within the region across availability zones. And we added a new functionality called as replication server, which also receives these redo log records and sends it across the region up to 5 regions in parallel. And on the target region, the replication agent behaves like a writer and sends it to the reader and the storage fleet for durability. So what it allows you to do is to connect to the reader instance for read scalability, and you have multiple regions available for disaster recovery. So with the Aurora Global Database, you can add 90 reader instances across 6 regions, 15 per region. So 15 on the primary region and 15 on each one of the secondary regions. And the key part is it doesn't impact the writer performance. You might ask how. It is because this replication server is behaving like a read replica, and it is sending the data across to a different region. And we already saw that the performance is pretty good, and we have some numbers to share as well. So the benefits you get are low replica lag because we have custom implementation of redo transfer, which honors the WAN characteristics, and the typical latency is less than 1 second. And if you want to failover between regions, you're able to do it in less than 1 minute. And this incurs a little bit more work than a failover within a region, but it's almost identical in terms of the underlying infrastructure. Instead of promoting a reader within a region, we promote it across the region and disconnect the replication. So we can do that within a minute. And we have a new functionality that we launched earlier this year called as write forwarding, where if your application connects to a reader instance in a remote region and issues a write, we transparently forward it to the primary region's writer instance, make the write durable, and bring back the results to you. So it is much easier for you to develop a global application. And we are working on failover, failback, so that you can fail over to a different region and fail back without recreating the replication configuration. Let's look at some performance numbers. First is binlog replication. This is the MySQL's logical replication capability. And you see on the y-axis the queries per second on the left side. On the right side is the lag in terms of seconds. As the QPS increases and reaches around 25,000 QPS, the logical replication by binlog is not able to keep up. The lag keeps raising unbounded, right? Simply, it's not able to keep up. Let's look at Aurora Global Database. You're able to reach 200,000 statements per second, and the lag is still less than 1 second. So essentially, your application, your database does not see any performance drop, and it's able to keep up. Why? Because we transfer only the redo log records using a storage system that understands the databases. Let's look at the write forwarding performance comparison. In this case, we are running a sysbench OLTP workload that is executed on a reader instance on a Aurora Global Database remote region, and we ran the same sysbench workload from the remote region talking to the primary region, talking to the writer. And the results are very consistent. If you use the write forwarding, you get better performance across the workload. So you can see that with the 100 threads, it's able to do close to 2,000 SQL statements per second. Whereas if the application talks directly to the writer across region, it's able to get around 1,500. Similarly, across various thread configuration, we're able to do much better by doing transparent write forwarding using our technology. So we talked about performance, scalability, availability, but you can achieve all of this only if you keep your database up to date. And we have made it much simpler now to keep your database up to date. We have successfully performed minor version upgrades to Aurora MySQL fleet on both 5.6 and 5.7 compatibility. And we did this for the clusters that have been opted for automated updates. And these updates contain several security and availability fixes. And I strongly recommend customers to opt for this type of automated updates. We released several minor versions for both engines 5.6 and 5.7 in 2020. We also released the ability to do major version upgrades. So if you have your database, Aurora MySQL database with 5.6 compatibility, now you can upgrade to 5.7 compatibility, which you should all take advantage of. Let's talk about success story. In this case, the example is Schoology Learning, which is a leading K-12 learning management system. The challenge that they faced was to handle 400% increase in usage caused by COVID, remote learning, right? So the solution is their application already used Aurora MySQL, and they added more reader instances, 15 reader instances in the primary region, 6 reader instances on a secondary region using Aurora Global Database. So their primary database performance still was not impacted with these many reader instances added. The result was Schoology was able to scale to meet the demands of thousands of school districts moving to remote learning. The numbers are astounding. 10 million plus students online, 1.9 million queries per second was executed on this database, 30 million rows read per second, and 8,000 writes per second. So the success here is the Schoology did not have to rearchitect the whole application. They just added more reader instances and used global database, Aurora Global Database. Let's talk about Intuit, similar success story for a financial management software for consumers, small businesses, and accountants. The challenge was they required a scalable, high-performance database to power the well-known TurboTax application across US during tax season. They used Aurora MySQL in US West, Oregon region, and replicated to US East, North Virginia regions, and enabled the global database feature. The 2018 and 2019 tax season went smoothly, with Aurora achieving Intuit's utilization and latency requirements throughout the US. I highly recommend you to check out the related sessions with Aurora Postgres and dive deep into Aurora storage and global databases. Thank you.